Before we look at some of the details of life on Earth and think about how we might apply that to the search for life beyond the Earth, let's take a brief tour and look at some of the basic facts about life on our planet, some of the things that perhaps we should know about as astrobiologists. Well, most of us are familiar with what we might refer to as big life, multicellular life. Here are some examples of the sort of creatures that you and I are familiar with on a day-to-day basis. But the first thing we should understand is that the majority of life on Earth, and when I say the majority, I mean most of the biomass, the biological mass of life on Earth, as well as most of the genetic diversity of life, is actually made up in the microscopic world, like these bacteria, a thousandth of a millimeter long. Tiny organisms that you can't see with your own eye, but you can see under a microscope. These dominate life on Earth, and they have dominated life on our planet since they first evolved. And we'll look at more of these throughout the course. Microbes are important because they're actually the most likely forms of life that we would find on another planet. Intelligent life is likely to be much rarer. Microorganisms were first discovered in the 17th century by a rather remarkable individual, Antony van Leeuwenhoek. Van Leeuwenhoek was a Dutch fabric maker, and he had a problem. He wanted to make high-quality fabric that he could sell to his clients. And in order to do that, he wanted to look at the fibers in his fabric to see what sort of quality they were and how he could improve them. So he went about inventing tiny microscopes. And you can see one of his microscopes here. They look very crude. You hold up a little lens to your eye, and with this device he was able to look at the quality of his fibers and improve the quality of them so that he could make better cloth. But Van Leeuwenhoek was a very curious individual, and once he had built his microscopes, he went about looking at the outside world to try and understand what might be out there in his garden. He started to look at samples of soil and samples of water, and as he looked at these, he discovered tiny animals, animalcules as he called them, that he began to write papers about. And you can see an image here of one of the first figures in one of the papers that he wrote in the 1670s. And it's rather remarkable because it shows the first image of microorganisms. Some of them are rod-shaped, some of them are little spheres, some of them seem to be spiral-shaped. And he even showed a microbe moving around. It's remarkable to us now that with such a primitive microscope, he was able to make out the different shapes of microorganisms that we're now so familiar with. But Van Leeuwenhoek did not understand that he had opened up a whole new science of microbiology, and he had in fact discovered the most abundant and the most diverse creatures on the earth. This science of microbiology would eventually lead us to searching for life in extreme environments and in fact provide the underpinning for what we now know as astrobiology. Since Van Leeuwenhoek's time, microbiologists have gone to all sorts of extreme environments, and we find environments with extremes such as high temperature, high radiation, extreme acid, and so on. And these extremes seem to define the limits of life, and as we go to greater and greater extremes, so we find that microorganisms are the only organisms that are able to live in these sorts of extreme environments. They become less and less diverse in general the more and more extreme the physical or chemical conditions become. These extremes define the boundaries of life on our planet. They define, if you like, the boundary of the biosphere. And you can think of the Earth as like a zoo surrounded by a fence of physical and chemical extremes. And these physical and chemical extremes define what we might call a biospace. A biospace we might refer to as the space bounded by physical and chemical extremes within which life in our planet lives, within which it inhabits the physical spaces of our planet. And I've shown here a very simple, conceptual, two-dimensional diagram of the Earth's biospace. And you can see this boundary of life, high temperature, pH, desiccation, and other extremes that define this outer layer of the biosphere. And provided you remain within these boundaries, you can be anything you like. And here's a weird collection of organisms that I've shown here that live on planet Earth within this biospace. But you cannot transgress the boundary. Once you transgress the boundary, you move into physical conditions that are far too extreme for life to be able to tolerate. Defining these extremes understanding where the limits of the biosphere are is one of the jobs of astrobiologists, and it's one of the tasks that astrobiologists have to do, is to find out what are the limits of life on Earth. Most of these extremes, as I've said, are dominated by microorganisms. Here's a hot spring in Yellowstone National Park, and within this hot spring, at a temperature of 80 or 90 degrees, there are microorganisms, organisms called thermophiles, heat lovers, that we'll see later on in this course. And these microbes inhabit these very hot volcanic environments that may represent some of the earliest environments on our own planet. And so by looking in these extreme environments, by looking at the limits of life on Earth, we can learn something about the possibilities for life in the early history of our planet and possibly volcanic extreme environments elsewhere in the universe. You might wonder, how many microbes are there on the Earth? I've said that they're the most abundant life form. Well, in fact, there are many, many microbes, 10 to the 30 in fact. And here is a slide with that number written down. 1,000 billion, billion, billion microbes on our planet. At least that's the estimate. But it's probably something around that number. Whatever the number is, it's very, very large, and it gives you some indication of how abundant microorganisms are on our own planet and why it is that astrobiologists tend to focus on microbiology, microbes, when they're looking for life on other planets. So where is this life on our planet? Where does it reside? This is a slide that shows you a geological cross-section through our planet. There's nothing particularly special about this. You can see the core of the Earth, the liquid core, and then the mantle and the lithosphere, the crusty surface on which we live. And what I'm now going to do is take away that geology and leave only the biology on our planet. And here is the biology of planet Earth, a tiny veneer of life on the surface and in the subsurface of our planet that inhabits planet Earth. Now, in fact, this line that you can see in the slide is 5 times larger than the real biosphere. I've increased the thickness of the line by 5 times, otherwise you probably wouldn't be able to see it on the slide at all. So you can see that life is a very thin layer on our planet. It's not everywhere. And you might wonder, why is that the case? Why doesn't the biosphere look like this? Why isn't the Earth filled with life? Why doesn't life live right the way through to the core of the Earth? Or why doesn't it look like this? Why isn't the biosphere a thick layer growing on the surface of the Earth and deep down into the crust and mantle of our planet and even below into the core? Well, the simple reason is that as you go down into our planet, it gets hotter. And the deeper you go, the hotter it becomes. And we think that the upper temperature limit of life, at least at the current time, is 122 degrees centigrade. So as you go deep into the Earth and you exceed that temperature, you get to places where life simply cannot live. And so the lower limit for life on our planet, the limit that defines the bottom of that thin layer of life that I showed you, is set by the high temperatures inside the crust of our planet. What about the upper limit of that thin layer of life? Well, that's set by the ability of life to survive in the sky. Clouds contain microorganisms. Next time you look at a cloud, you can think of it slightly differently, as a bus carrying microbes around the Earth. But in fact, it's a very difficult place to live. Clouds are very cold, they're exposed to solar radiation, and there's not much food there. As you go higher up into the atmosphere, it becomes more and more difficult for life to grow. Certainly, some microorganisms can survive high up in the atmosphere, but it can't really multiply. And that height is probably something like 3 kilometers in the atmosphere. Beyond that, it's very difficult for microorganisms to grow. So the lower limit and the upper limit of the biosphere are not exactly known at the moment, and scientists continue to study life in the atmosphere, and many scientists are studying life in the deep subsurface to try and understand the lower depths of the biosphere. But probably we can say at the current stage that the biosphere is something like 10 to 20 kilometers thick. But even if that number changes quite a lot, even if it was to double or even multiply by 5 times, it doesn't really change the fact that life on Earth is a very thin veneer on the surface and near surface environment of our planet. So you might be thinking, what does all this tell us about the search for life elsewhere? Why would I want to know this if I was searching for life on Mars? Well, understanding the limits of life on our planet understanding where it lives, the depths of the Earth in which it might grow and reproduce, and how high it might live in the atmosphere, and the physical extremes that it can tolerate, tell us something about the possibilities of life beyond the Earth. It helps us search for life on planets such as Mars. And if we go back to this conceptual diagram that I've shown you earlier, I think it's true to say that one of the most remarkable advances in astrobiology over the last 1 or 2 decades has been the realization that some environments on the Earth, environments that are very extreme but nevertheless harbour microorganisms, have similar physical and chemical conditions to environments that we find on other planets. Just one example is very cold and salty environments on the Earth. For example, if you go to Antarctica and you find a very cold, salty lake, you can find microorganisms growing in that environment. And we also know that the planet Mars has cold, salty environments. And the question is, do those environments contain life? Well, at the moment, we don't know. But the point is this, that some physical and chemical environments on other planets seem to overlap with the biospace of life, the space in which life might be able to persist. And so by knowing the limits of life on Earth, by exploring the outer boundaries of our biospace, we can improve our attempts to search for life on other planets. So what have we learned in this talk? Well, hopefully what you've learned is that life is abundant on the surface and just underneath the surface of the Earth. But you've also learned that life is bounded by physical limits and extremes, and it occupies a biospace. And understanding the limits of that biospace is the job of astrobiologists, to define the limits of the biosphere. Although life is abundant, it also means that it occupies a very small part of our planet, and we would expect that to probably be the case on other planets as well. We've also learned that some physical conditions that are suitable for life may overlap with conditions on other planetary bodies, driving an interest in the search for extraterrestrial life. And so by understanding the limits of life on Earth, we can assess better the habitability and the prospects for life elsewhere. And finally, you've learnt that microbes are the most abundant form of life on the Earth and usually occupy the most extreme environments on our planets. These microbes are called extremophiles, from the Greek philos, to love, extremophiles, microbes that love extreme environments. And later on in the course, we'll have a look more at these extremophiles and some of the environments they inhabit.